Hi, Arpit. Thank you so much for being on my channel and taking out time. I know you are already juggling with a lot of things, so thank you so much for taking out time.
Thanks so much, Sukhat, for having me.
Yeah. So, for a start, if you would like to give a bit of your introduction yourself.
Okay, so from my side, hey folks who don't know me, my name is Arpit. I love exploring entire domain of engineering, be it around core engineering, be it software engineering. I just love exploring it. That's the only thing I know. I've been
Mm-hmm.
in industry working for last 8/10 years if you count masters or not, depending on that. I graduated in
Mm-hmm.
2012 from the government college in Pune, then did my masters
Mm-hmm.
from Triple IT Hyderabad, effectively started my career in 2015. I was part of, like, I joined Practo, Amazon, Unacademy. At Unacademy, I was there for 5 years. I
Mm-hmm.
joined as an IC, left as a director. So seen both sides of the spectrum. Seen like worked as an engineer, worked as a leader. Now basically
Mm-hmm.
very recently made a switch to Google, working on some
Mm-hmm.
good projects there. And but apart from that, built my programming language, built my database, built so many prototypes. So I just love exploring this entire domain. So all in all, a nerd that if you like
Mm-hmm.
core computer science, you'd love talking to me. Simple.
I've seen your YouTube channel. You are doing a great job, like going into depth of topics. So today also we have chosen a similar in-depth, a topic in which we can go quite in depth. So we are going to compare the SQL and NoSQL databases. There are a lot of myths in the. I see that people just give a small differences, but I think they are not enough, and there are a lot of things to explore. So yeah. So what are your views on this?
uh, so it's something that I can rant about for hours. What a lot of YouTubers say, what people think NoSQLs are. There are so many misconceptions floating around. First of all, whenever I
Yeah.
speak to someone, it's like, I'll use NoSQL because SQL doesn't scale. I'm like, what? What? SQL doesn't scale? Since when did this happen? So
Yeah.
this is the most popular misconception, that
Hmm.
it's not about that a particular kind of database doesn't scale. It depends
Hmm.
that a kind of database doesn't scale with a particular constraint. If you
Hmm.
drop that
Right.
constraint, it would scale. And this is
Hmm.
something that I keep telling every single person I meet who wants to talk to me about SQL versus NoSQL. So that's the
Okay.
common
Hmm.
thing. Like, then this
Hmm.
is where I feel we all need to understand that what makes a database. It's the
Hmm.
underlying storage engine of the database,
Yeah.
right?
Right. Right. Right.
And given that the flexibility of the storage engine, so depending on what
Hmm.
storage engine the database use and how
Hmm.
you are exploiting it, you will get that
Hmm.
kind of performance out of it, right? If
Yeah.
I talk about NoSQL database, with
Hmm.
NoSQL database, what typically happens is people say it doesn't scale, or sorry, with SQL databases, people say it doesn't scale. But
Hmm.
instead of asking that, it should be more about why is NoSQL database able to scale? It's
Yeah.
basically
Right.
by default sharded and whatnot, right?
Hmm. Hmm. Hmm.
So
Yes. Yes.
why
Yes.
is SQL not sharding? If you shard SQL,
Hmm.
it would scale,
Yeah. Right.
right? And the kind of performance you would get on single node depends on the storage engine that's there, right? So
Hmm.
it all depends, to be honest, but it's all about how well you know the database that you are working with, so that you can tune those
Hmm.
parameters and get the max out of it. So yeah, we can dive deep into each one of this. So have
Yeah.
plethora of
Hmm.
experience doing and
Yeah.
managing
Yeah.
things and hitting and shit hitting the fan in production. So been there, done that, seen
Yeah.
that.
Yeah. So I think let's first start
Hmm.
with SQL databases,
Hmm.
their internal structure. Like you talked about, like we should know about how are things happening on a single node
Hmm. Hmm.
when a database is on a single node. So what are the internal structure? What is the internal, mostly data structure of a SQL database? How is the data actually stored on the disk?
It's a very common belief that SQL databases use B plus tree to store the data.
Yeah.
Not true.
Okay.
Let's start with that.
Okay.
Not true.
Okay.
So B plus tree is one of the implementation, right?
Yeah.
But
Hmm.
you can change the storage engine. So by the way, you can write your own storage engine within 3 hours, right? It's
Hmm.
not that
Okay.
difficult. You just need to write a bunch of C++ code, implement a bunch of methods, and you can write your own MySQL storage engine. MySQL
Okay.
documentation itself has exact steps through which you can write your own storage engine. So now what you can
Okay.
do is, instead of, let's
Hmm.
say, you storing data in B plus tree, You change it and keep data in memory. What's the problem in
Right.
that? Nothing. You store the data in raw CSV file, right? So now, but the most common out of the box things that come out of like basically when you install MySQL is the engine. It may be my ISM engine or it
Okay.
could be the InnoDB engine, right?
Mm-hmm.
Now these two popular implementations, they store data in B plus tree. So that's why a lot
Okay.
of people say, and I'm talking with respect to MySQL, but it's true for all,
Yeah.
that
Yeah.
a lot of
Yeah.
databases, the default engine that they start with, they store the data
Hmm.
with respect, like they store the data in B plus tree on that disk, which is why people in a very general sense think that SQL databases store data in B plus tree. But
Yeah.
again, it depends where the data is stored depending on the storage engine, right?
Okay.
And the reason the data they store in B plus tree, because it gives you log and lookup to no
Right.
matter which row you are accessing, and which is what makes it ultra special, that no matter which row, it basically is improving your pointed lookups. When you are looking up a particular row by a particular ID, you would get order log and time reads, and which
Okay.
is exactly what you need from a database to have predictable performance, right? And which
Got
is
it.
why
Yeah.
most commonly B plus tree is used as an implementation thing for a normal relational database.
Yeah. Okay. So, and now coming to the NoSQL databases. So, like you mentioned that the underlying engine can be same for both
Correct.
SQL and NoSQL.
Correct.
Yeah. So for NoSQL databases, what is the mostly commonly used data structure?
So the best and the worst part of a NoSQL database is that there is no standardization. So with relational database, so a database cannot claim to be a relational database if it does not support ACID, if it does not support rows and tables, or sorry,
Yeah.
basically rows and columns. But
Columns.
NoSQL says, hey, we don't follow any standardization. Depends. I can be key value store, I can be graph, I can be document, I can be data
Document.
warehouse, I can be columnar, I can be anything. Right? So
Yeah.
now what is NoSQL? So if I were to put all sorts of databases on a landscape, I can see that SQL only accounts for 5% of database, but it still rules the industry, right?
Yeah.
And there
Yeah.
are plethora of databases that solve very niche problems, and they
Hmm.
do it really well.
Right.
So which means that someone who wants to solve or who wants a solution to a particular kind of storage slash access pattern would have to pick that kind of database. So there is no
Okay.
one answer. With SQL, you can generalize to some extent and say कि B plus tree is used, but with NoSQL, you cannot do that. With NoSQL, you have to be in the position that say, hey, I want this kind of use case. I'm using this kind of database. So now what's the underlying storage of that? Because there is no
Okay.
standardization. Because if it was standardized, then like SQL has a SQL layer through which we query, NoSQL would also have something like that. But there is nothing because there is no standardization. It is very open. So depending on the needs that you have, you would see that kind of storage engine. So key value has
Okay.
different, document DB would have different, graph database would have different, right? Columnar
Okay.
DB would have totally different. And now there
Yeah.
is a plethora of databases which venture into decentralized database category. They are different. There are hybrid databases. There are new SQL databases. So many are
Okay.
there, right?
Yeah.
And
Yeah.
then in-memory cache and those worlds are different totally, right?
Yeah.
So it depends.
So if we consider like suppose MongoDB for an example, I'm not sure data structure it uses to store the data.
The highlight of any document DB is that it is very close to relational database. So document DB make it simpler for people to migrate from relational to non-relational world, right?
Yeah. Yeah.
So
Right.
document DBs are very close to the functionalities that relational databases provide with a bit of change in their modeling layer, right? Even I'm not sure about a lot of internals on MongoDB. The engine that they use is called as Wire Tiger for the open source
Yeah.
version.
Right. I got.
So I have it bookmarked for a very long time that I want to dive deep into those internals, but I didn't get time. But if I do, it will be there on my channel hopefully someday.
Yeah. Yeah. So, like we talked about, so it is possible for a NoSQL database to also have a B plus T data
100%.
structure, right? Yeah.
100%. Yeah.
So now, suppose we have two databases, SQL and NoSQL, both have the same underlying data structure, which is the B plus trees. So what differentiates them on the top level?
The thing that differentiates them are the guarantees that they offer. So
Okay.
when a database developer or a database researcher actually conceptualizes a database, he or she would conceptualize it in order to solve a particular problem, right? So to target that particular niche. Now, depending on which, he or she would decide, ki, hey, I need A, B, C, but I don't need D, E, F. So now,
Okay.
because there is no standardization per se in case of NoSQL, the beautiful thing is that it depends on the database developer on what kind of constraints he or she would want to drop and what he or she would want to gain. So it's very
Okay.
much possible that you might just create an embedded database and not worry about a centralized DB. Like for example,
Okay.
that is how RocksDB, LevelDB were conceptualized. That hey, I want an embedded database, I don't want a centralized database, right? But some database developer thought, ki, hey, I'll store everything in RAM. I don't want to store anything in disk. It can be used as a cache, and which is how basically Redis worked out. So now it really does not matter what underlying storage engine it is, or how the data is actually stored on the disk or in memory.
Okay.
The kind of guarantees that the database would need to offer would depend on the kind of niche it wants to operate in. Right? I don't
Okay.
totally depend on that. Like some databases would be distributed, some database would be centralized, some databases would be embedded. Right? And it
Right.
totally depends on that. So because of which you are expected to know a lot about databases because there are hundreds of options to choose from.
Yeah.
And
Right.
then that becomes the next big problem, ki, arey, how to pick one over other.
Yeah. So, like, at what level is the change comes like the data is stored in the form of JSON format and the data is stored in the form of rows and columns format. So, the way we see it, it is in the form of that, but internally it is in the form of a B plus tree, for example. So, at what layer does this distinction and mapping happens?
Okay, great question. So, what happens is it really does not matter. Like in any database implementation, a database typically comprises of 5 to 6 independent abstracted layers. So first
Okay.
is how it accepts the query, then how it parses the query, then how it optimizes the query, then how it creates an evaluation of that query, then how it actually
Okay.
evaluates the query, and then how it talks to the underlying storage layer, and then the actual storage layer itself. Right? Now there are many layers, and each one of them has a contract. Right? And you can literally plug out one and put in your implementation, which is why at the beginning of our discussion I said that you can literally write your own storage engine and basically plug it with MySQL.
MySQL. Okay.
So where these things alter is in most cases a database or a person who is conceptualizing a database would want to make it really easy for people to absorb their database, which is why you would see JSON as a very, very, very preferred format for people
Yeah.
to build database. So basically Firebase is using almost JSON. Basically MongoDB is pura JSON based, but internally MongoDB is not storing JSON, it is storing BSON. It is basically binary form of JSON.
Yeah. Right.
You may have a columnar DB that is storing data in a B plus tree node, in which JSON is basically stored, maybe let's say an hyper compressed protobuf format. You can very well do that. No one's stopping you from doing it, right? So the way this distinction comes in, that where it starts to land up, the idea is pretty simple. At every layer, keep that abstraction handy so that you can literally plug and play and make your database better. Right? Now, here, whenever a NoSQL database developer would think, it was all about what problem are we solving, because a database is as performant as its storage layer.
Okay.
Because if you are able to fast read or do fast write, because if you are doing, let's say, a time series DB, you need to store it in a certain way so that those kind of queries are very optimized, right? Because
yeah.
for time series databases, it would be like you need to have very efficient range based queries, right? Plus, there would be millions of data points, which means you can do run length encoding and a bunch of comparisons on that. So your data structure, your on-disk data structure would have to be optimized for that. Right?
Okay.
This is the
Got it.
first level of distinction that comes in, that the problem that my database would try to solve, your underlying structure needs to solve that problem really well. Right? That is one.
Okay.
But it does not dictate what end user sees. Because you can write a
Right.
layer that converts this into something which is usable by
User.
or rather which is basically easily consumable by the consumer. Right?
Right.
But the storage engine is the most important layer of the database.
Okay.
Whatever suits your need, you go that. But then your database, if you expose the complexities of your storage layer at the top, then things would go berserk because they might not know encoding and compression and whatnot. So
Yeah.
they have to make it very simple. So you may see JSON at the top, but beneath the lines, it's all messy, highly compressed way of storing things.
Okay.
So, yeah, go on.
What would a node of a SQL database contain? Like B plus tree node, if we consider a single leaf node.
Okay,
If it
in
is
a relational database like MySQL or Postgres, it would contain the
Yes.
exact row that you are storing.
Okay, complete row.
The
Okay.
complete row is stored in the B plus tree node. Right? Literally, because in SQL or in specifically in case of, let's say, MySQL or Postgres, all the columns are having fixed widths. Right? So it would exactly know how much data it would, how many bytes would it require to represent one row, and that's how it would determine the size of the B plus tree node. It would need n minus one. It would need basically n plus one pointers to store the child and the left and the right, and you link them. Apart from that, the actual data would be stored in the B plus tree node. It may not be one row. It may be 3, 4, 5, 6, 10, 15 rows. So how many rows it can fit? It would fit into that. But given that it's a fixed width, you would exactly know how many rows fit in one node of the B plus tree that you are storing.
B plus tree.
That's exactly what is stored on disk in a B plus tree node.
Okay. And in the case of something like MongoDB, it will be complete document.
It will be completely document, which is binary encoded form. That is exactly stored. But obviously, not one document, one file. You may build a database that stores one document as one file. But what MongoDB would do is it basically merges them, or a bunch of documents stored in a certain format, and then indexes. So it would have its own indexing scheme. It would have its own something very similar to B plus tree. May not be exactly B plus tree, but something very similar to that gives them very predictable reads and writes and efficient access.
So now as we are talking about indexing only. So let's talk about how indexing would happen for a SQL database and a NoSQL database.
Okay. So indexing concept, irrespective it's SQL or NoSQL, it's exactly the same.
Same.
There is no difference. The idea of indexing is to make reads faster. The way you make reads faster is by making the amount of data you need to look up smaller. Right? So for example, if you don't have any indexes, you do, obviously that's how humans would also do. If you don't have, like if you have a gigantic word dictionary and there are no indexes and you are looking for something, you would literally, and if the words are randomly ordered, right? Then you would literally go word by word to find your word, and once you find, you get the meaning. That's exactly what your database is also doing. Right?
Yeah, scanning.
Right? But then the next step you say, hey, let me just order it by primary key. In the word dictionary, it is word. Your order by word. So now you know how you go, but there is no index. So you still go line by line or word by word, but at least you know, okay, this is where I would find that word. But then comes indexing, which says that, hey, all A start from here, all B start from here, all C start from here.
Okay.
That is exactly your index. So the indexed value and the offset is what you store in the index. Right?
Okay.
And now the size of this index would be what? If you are talking about word dictionary as an example, there would be 26 entries. Each entry would have a character and a page number. Right? So the indexed value, in that case, it is 1 byte. And offset, which is integer, so 4 byte. Each entry is what? How much? 5 bytes. There are 26 entries. So 26 into 5, whatever that is, like 120, 130 something, right? So 120 bytes. So that's your index size.
Okay.
This you can fit in RAM, right? So next time the word lookup comes in that, hey, I am looking for cat. So you would do this, you have loaded in memory hash table. You go through C, find this page number, you go to that. And you start doing a linear scan there. Right?
Okay.
So what we created is a sparse index. Right? where you
Okay.
are not having all the entries, all the words over here, because you wanted to keep the index size smaller. Right? But then you can create a dense index where all the words that you have, you are storing all the words in your index. And let's say if there are, let's say 700,000 words, right? So 700,000 into 5, right?
Okay.
Those many bytes you would record, which turns out to be 3.5 MB, right? So your index size become 3.5 MB, and so which holds this thing that this word is present at this page at this offset, right? So that is exactly what you store in index. So
Okay.
no matter which database you are using, the concept of indexing would remain same. Either you have a sparse index or a dense index or a hybrid of both, right?
Yeah.
But
Right.
the idea is to make lookups faster so that you can go to that location as fast as you can.
Got it. So in both, like we can choose the key we want to make the index on in both the types of, yeah, and on the basis of that it will create the index. Got it. So now one question which might come in a lot of people's minds is, why are we not able to do joins in a NoSQL database, but we are able to do that in SQL database, even if the data structure in which they are stored is the same?
So join is not the property of the underlying storage. It
Okay.
comes on the compute side. That hey, you can do, by the way, you can do joins on distributed database. It's just a little
Yeah.
expensive, right?
Expensive, yeah.
Right? Because
Yeah.
you have to do on network data transfer. So ideally, what join is? Join is basically you have two tables and you have a join key and you are joining those two tables on that particular key. Now, here, if the data that you are joining, so the two tables that you are joining, if they are on the same data node, you just have to read from the disk and join them. But if
Right.
a table is present in one machine, other table is present in another machine, which means your data is distributed, your database is sharded.
Distributed.
Now, if you are joining it, which means there has to be one place where that either this data needs to be copied on the other machine, or the other machine's data needs to be brought in one machine, right? Or move both into some third machine, irrespective of what you want to do. But idea is
Yeah.
that for you to be able to join the tables, the data needs to be there on one machine. Otherwise, you cannot
Okay.
do join. Otherwise, it would be an approximate join. That is also
Right.
a class of joins out there. Very few people know about it, but you may do approximate joins if you want to. But ideally, when you are joining, you want the correctness. You'd have to bring all the data in one machine, and then you do joins on top of that, right?
Okay.
So with sharded database, with distributed database, you would have to pull all the data that you're joining on one machine, and then you do join. So now bringing in data over the network to this is very costly.
Yeah.
Which is why people don't do it. Which is why people just avoid and say, we can't do joins in NoSQL databases. That's not true. You can do it, but it's
Right.
just expensive.
Yeah, you have to bring the data yourself and then do the join, whatever you. Yeah. And the SQL does it for itself.
Because
on the
SQL
above layers.
assumes that the data is present in single node.
Single node, yeah. Yeah. So that brings us to the sharding question. So like the tables which have to be joined, they have to be present on single nodes. So now, how would sharding differ for a SQL database and a NoSQL database?
Sharding is same for both.
Okay.
Sharding is same for both. So now it depends if you're doing horizontal sharding or vertical sharding, right? If you're doing horizontal sharding, then it does not matter if it's SQL or NoSQL. If you'd want to join or access the data across it, you have to have data on that same node. If you don't have it, you have to make network calls, which would be expensive, right? But with SQL, you may also see a tendency of people doing a vertical sharding, which means few tables,
Right.
like few tables itself in one node, other set of tables in another node. So frequently joined table you can keep in one node. While frequently joined table, like the other class of table can be in another node. This way you're still
Okay.
maintaining that condition that all the data that you need to join together, it lies in one node. So vertical sharding way you can get this benefit, where
Okay.
frequently joined table you are keeping it in one shard.
Hmm.
You get it. But if you are doing horizontal shard, which means that data would be present in hundreds of nodes and there is no affinity as such where your data may lie in any node, then there is problem. Then you have to rely on network copy of the data and then you join and then you do that crunching on that.
Yeah. Yeah. So a lot of people in SQL to get rid of this problem, what they do is they do Geo Sharding. So the data which is kept on one node, it will be joined with that only. So how will that work? So because the table is same, but you are kind of joining on a subset of the data.
Yeah, table is same, I'm joining on the subset of data, but still it's a partial join. It's you. So which means you are giving up on the correctness. So you might be miss out on some data,
Okay.
right? Which
Yeah.
is exactly a class of approximate joins come in. So what
Okay.
you are doing is you are joining on whatever data you have handy. You are joining on that. Given this that the partial data, like basically whatever data you have available, you are joining on that, which means that it is okay for you to miss out on other rows which are yet to come to this particular data node. Right? You should be okay with that. And in most cases, it is. For example, if you are accessing Twitter or any, and I'm just giving example, I don't know their internals. I'm just using them as an example that
Okay.
Twitter is a geographically distributed application. Do you see tweets from all the people in another geography? Very
No.
difficult. Right?
Yeah.
They
Very
would
tough.
know that there would be few people. For example, Elon Musk, he would
Hmm.
have asked his engineers to literally control C, control V all of his tweet into all the regions, all the data centers that they have. Because it's very likely that everyone from the world is accessing the tweets. But if some
Okay.
random person who no one knows about is sitting in the US and tweeting it, would you want to copy the data of his or hers into every single data base? Not really. Right?
No.
So
Okay.
depending on the criticality, depending on what you are powering, you may choose to do cross-region replication of data, and then you build systems
Okay.
and then you build systems around it. Otherwise, you are happy doing and if you're happy doing partial joins, go for it, right? It's because that gives you speed. So what you're trading off is you're trading off correctness with speed.
Okay. Okay. So basically, they might have some kind of system that if some popular personality is tweeting, then this data has to be replicated across the clusters. Yeah.
Yeah.
And also, some people can do on the basis of language also. Like,
Correct.
if some,
Yeah. So it is all heuristic, right? Language, basically language, user clustering, random parameterization. You do basically collaborative filtering to merge them. Put any technique, right? And
Okay.
you decide what works well for your business.
Okay. Got it. So in NoSQL databases also, you can simply just put the JSON documents or the key,
Yeah.
different keys in different nodes that you have,
Yes.
right? Like when we talk about MySQL databases, we always come across thing called that these are kind of master slave architecture. These are built on a master slave architecture. So would you like to talk more about how the architecture of a SQL database work?
So with respect to like any replication, and it's true for any replication. So it's basically master replica, where what happens is when the write happens on the master, it needs to be replicated to the replica. And the reason we do that in order to scale the reads, because replica will not accept writes from anyone else. It would only accept writes from the master. And this would be an asynchronous replication. So you have to be okay with the replication lag. And this is typically done in order to scale reads. Right? So master
Right.
is the one that is accepting almost all the writes,
All the
and
writes.
then the reads are asynchronously propagated to the replica. The way with MySQL it happens is using bin log. So MySQL bin
Okay.
log replication, it leverages and it streams the output, or rather the replica pulls it from the master periodically and keeps applying those writes on it. Right? This way, whatever write happened on the master, it gets replicated to replica. There would be some replication lag, be it few milliseconds, few seconds, few minutes, few hours, even few days, right? But you should be okay with that. So you typically have alerts on those that, hey, what's the replication lag that I would want to work with? What is okay for your business? And that should be an okayish limit for you. But then that helps you, because in most cases, the read to write workload ratio is 99:1 or 90:10, if I may not exaggerate.
Okay.
So you are more likely to get reads than writes. So you typically optimize for that. Hey, let me just have a synchronous replication setup through which I'm replicating the data. Once I get the data, I basically keep querying on this DB instead of the master DB. Right? This way you save master's bandwidth, network bandwidth, CPU computation, memory, and disk, and use the replica to get your queries answered.
Okay.
And same thing
So,
goes for NoSQL. Control C, Control V.
NoSQL. Yeah. So, but in this, in SQL databases, mostly these are like strongly consistent, if I'm not
No,
wrong.
they are not strongly consistent. No.
Okay, they're also not.
And actually, it's configuration, but no one does it strongly consistent because it would slow down. It would massively slow down the throughput of a relational database. Asynchronous with almost near zero lag is what people go for. It's not strongly consistent.
Okay, it's not some. Okay, so it is possible that when you write, you might not get the same data
Yes.
when you read.
Yes.
Yeah, and same goes for the NoSQL databases. They are already eventually consistent.
Yes.
Yeah,
Yeah.
yeah, yeah. So, what are the other different types of architectures that we can build MySQL or NoSQL databases? So, has it always has to be a master-slave architecture, or we can go for something like peer-to-peer?
Peer-to-peer, no. Multi-master, yes.
Yeah, multi-master.
A multi-master you can definitely do. But the problem with multi-master is how would you handle IDs? Like, for example, you have auto-incrementing ID columns. You have same table in two database, and both databases can accept writes. Then both databases have their individual counters. Writes come to it. Let's say my counter value is 100 on both, and now you have started a multi-master application. Write came over here, 100 became 101. Write came over other database became 101. Gone. So then that's not unique. So you have to drop auto increment columns from all the database, have your own ID generators in place and build it. So multi-master application, the biggest challenge with that comes in is how do you handle conflicts?
Conflicts. Okay.
Massive problem, right? So which is why when you build when you go for a multi-master with MySQL, Postgres, or any relational database, or even non-relational database, you need to know your business use case really well. That how conflict resolution would happen, because there is no generic conflict resolution technique. It totally depends on the use case
Business
that you are
logic.
solving. Right? That in some cases it is okay to override the last write. Override the previous write, and basically last write wins in that case. In some cases, the first write wins. In some cases, you may have to literally concatenate them. In some cases, you may have to not accept any. Right? Now, how do you handle it? Depends on the business use case that you have. Right? But with multi-master, you have to do it. There is no way out. Right?
Yeah.
But then you have to write your conflict resolution logic and you have to inject it in your database, and then you would have a multi-master application in place.
Okay. So let's now talk a bit about distributed database. So in that, mostly there should be multiple masters and in different types of. So how would a distributed database look like?
No, so distributed databases are basically, so masters in typical distributed databases, the masters are independent. They're not multi-master.
Yeah, independent. Yeah,
if masters are independent, there is no problem because it's basically shards. Right? Basically, each database would hold a mutually exclusive subset of data. A request, so you would have a proxy layer. Request comes to proxy. Proxy knows where to forward a request to. Request is forwarded to that corresponding node, and it stores and queries and does basically whatever it has to do with the data. Right? So that is a much simpler problem, and that's why you would see shards, like a sharded database is typically an example of a distributed database.
Right.
But as soon as you enter the world of multi-master, that hey, I may have overlapping copies of data. That's where a conflict resolution kicks in. And you have to be aware that how do you do conflict resolution in that case. But then in any case, you have to be okay with the replication lag and the complexities that come with it.
Okay. So suppose in a SQL database, as we have to join with the complete tables, the data is sharded across different clusters, different master slave node clusters, and we have to join, like you talked about on the business layer. So how would a complete join would happen across different?
All the relevant data from other databases will be brought onto a single machine, and then the join would happen. So you would have to wait until all the data from all the nodes is brought into a single node. So the typical flow, obviously it would vary with the, but the typical flow would happen that the proxy would send request to one of the nodes, right? Depending on whatever logic the proxy has. Now that node becomes the orchestrator, which means that node's responsibility is to talk to every other node and bring in all the relevant data. Once all the nodes sends all the relevant data for that corresponding entity, let's say you are joining on a particular ID equal to something. When you have all the data from all the nodes to this database, then this orchestrator node would do a join within that database. Right? And then it would compute the result, send the result, and then discard all the intermediate data that it created. right? This
Yeah,
is how it happens.
yeah, but this will kind of become impossible for to bring all the data into the main memory.
Now, so
Don't know the-
you don't need to bring data in memory, right? So
Okay.
you can
Yeah.
still do a
Okay.
disk. You do disk
Yeah.
read. You read on you can read the data that you brought in chunks by chunks and do join. You don't have to bring all the data in memory so long as you have a way to group them, which anyway you would when you are writing a join
Need.
query. So that was never a problem. But the
Okay.
problem here would be bringing in all the data from all the nodes because a node might be unavailable. There might be network partition. There might be an issue that one of the node is slowing things down for you. So then your response time would shoot up. So which means that this kind of query cannot be used to serve real-time use cases.
Okay.
Right? So these are all typically big data works exactly like this. Right? But you are okay spending more time because you are crunching in more numbers. So that's why you don't do it in a request context. So given a request, I want a response, and while computing the response, I want to move all the data here and there and compute it. Very long process. No one does it. So that's why these are all analytics workload.
ETL.
They happen like
Got
this.
it. Right. So now we have kind of talked about a lot of things. So for what use cases would you say? Is there a specific line that you can draw that for these use cases we'll definitely go with SQL databases, and for some different use cases we'll go with NoSQL databases?
The strength of relational database is its ACID compliance. Right? No matter how many NoSQL databases come and they say ki we are ACID compliant, I don't trust them. If they are sharded, I don't trust them, because then if they are sharded and they claim ACID compliance, which means they are going into distributed transactions, which means they are slower. So
Slower.
I don't trust them. If your data can reside on one node and you need strong consistency, no matter what, because you can guarantee strong consistency easily when your data resides in one node. Right? If your data is distributed, then you can easily guarantee eventual consistency. Right? So I personally would prefer relational database when I need ACID compliance, strong consistency of data. Right? Because I am working on an assumption, I'm working with an assumption that all my data resides in one node. When it comes to non-relational database, my by default assumption would be that my data would be distributed. And I'm giving a very, very generous assumption, given that I have plethora of options to choose from. There are embedded databases, single node databases, whatnot, right? But if my database is distributed, I would go for a distributed database when where my volume of data that I'm operating with is going to be massive.
Okay.
For example, messaging apps. When I would want to store messages very easily would explode. So I would want shards there by default, right? And I don't need ACID compliance with messages. They are just there to store, right? So that is the kind of use case where your data explodes, is where I would go for a distributed database, and where I need strong consistency within a single node, and my data can reside in a single node, I would go for a relational database. So because ACID is the strength of relational DB, while handling massive data, distributing the data across nodes is strength of a non-relational distributed database like MongoDB. So I'd go for that.
Okay. Okay. So, but this property, like when you have to store all the data on a single node, that rarely comes like when you have to.
No, when you have small chunk of data, then when you have data whose size is 1 TB, 2 TB or 5 TB. 5 TB of text data is still huge. Right? 5 TB of text data is anyway, if that's the case, then you can very well do it with relational DB. Right? You don't need to overcomplicate your situation with shards and all. Right? At the end, your business should function. No matter what. Right? What matters to you is the business that you with your engineering skills are driving. It does not matter what fancy database you use. Right?
Yeah, so but in this case, like suppose if it had read replicas also, so like we discussed that it will still not be strongly consistent.
No, but read replicas are anyway not strongly consistent, because you cannot wait for your write to be propagated to the replica and it sending you acknowledgement and then you claim that the write is done. You can build a system. You can have a replication you can have a synchronous replication factor of 2, which means you are doing 2 writes and then you claim that the write is done. But if you do it, you are compromising on throughput. If you need high write throughput also, you need distributed also, you need strong consistency also, then you can't get it.
That's not,
You get some, you lose some. And that's the thing that senior engineers are supposed to do. That they make people aware
trade-off.
That everything in life, everything in computer science, everything in software engineering is a trade-off. Now you need to pick your battles and win it.
Yeah. I think we have covered a lot of different things,
Yeah, we did.
and yeah, these were the mostly questions which I had in mind. Anything extra if you would like to talk
No,
about
no, all
with
good,
respect?
all good. All questions were great. We really touched upon the massive database spectrum.
Hmm.
And while talking about it, I realized ki, yeah, I've worked with a bunch of them. To be honest, one thing that I would always recommend people to not have
Hmm.
biases, to not just go by words that SQL
Hmm.
doesn't scale, no SQL scale. So many people talk about it. No, that's garbage.
Right. Hmm.
That's utter garbage. I can
Hmm. Hmm. Hmm.
scale SQL database just by dropping constraints. If I don't have foreign
Hmm.
key constraints, then my SQL database
Yeah.
is equivalent to a no SQL database, right? So
Yeah.
there is
Yeah.
no
Right.
hard and fast thing. It's just that you just make one database feel like other, and
Hmm.
you get the benefit out of it, right?
Yeah.
So just
Right.
explore, like, don't have biases towards certain databases. Every database is good, every database is bad. Like, everything is straight off, right? So you just need to know
Yeah.
which one to pick, when and where and why. If you do
Yeah.
that, that's good.
Yeah. Yeah. I think that's a great advice, and this was a great session. Thank you so much again
Thanks,
for taking
thanks
your
so much,
time.
Sukat, for having me. It was fun having a chat.